Having introduced Boolean algebra, we can now define expressions and functions within it. A Boolean expression, also called a logical expression, is defined similarly to expressions involving natural numbers. It is a combination of constants, 0 and 1, and variables connected by means of the three logical operators. Formally, Boolean expressions can be defined as follows. The individual constants 0 and 1, as well as individual variables, constitute Boolean expressions. If G and H are Boolean expressions, then so are their sum, their product, and the negation of each one of them. There are no composition rules beyond those just stated. An example of a valid Boolean expression is x and y and z, or not y not z. In contrast, x and or y is not a valid Boolean expression, as it contains two operators in sequence, which is syntactically incorrect. A Boolean or logical function of n variables is defined as a function whose domain is the Cartesian product of the support set taken n times and whose codomain is also the support set. Since the support contains only two elements, 0 and 1, a Boolean function can be represented using a truth table. This table enumerates all elements of the domain and associates each with its corresponding output value in the codomain. For example, consider the truth table of a function with three variables, a, b, and c. The table consists of 8 rows, where 8 is the result of 2 to the power of 3. Each input combination is associated with an output value of either 0 or 1. Let us now study the relationship between functions and expressions. Every Boolean expression involving n variables defines a unique Boolean function over those same variables. To derive the truth table of the function corresponding to a given expression, it is sufficient to evaluate the expression for all possible combinations of values that the variables can assume. Here is an example. The expression not AB or AB involves two variables. Therefore, there are 4 possible combinations of values that can be assigned to A and B. We compute the value of the expression for each pair and fill out the corresponding truth table. The reverse process from function to expression is more challenging. Indeed, an infinite number of expressions can represent a given Boolean function. Here is an example showing 2 possible expressions corresponding to the same function on the left. The first is not A and not B and A, and the second is simply A. The key question, which will be fundamental in the first part of the course, is therefore, how can we generate an expression from a given function? We will begin exploring this topic in the next lesson. We conclude our discussion on the relationship between functions and expressions by asking, when are 2 expressions considered equivalent? 2 expressions are equivalent if they correspond to the same Boolean function, that is, if they share the same truth table. As an example, let us prove that the 2 expressions from the previous slide are equivalent. We compute the truth tables for both expressions. For conciseness, we present them side by side in a single table. As we can see, the 2 columns representing the output values of the 2 expressions are identical. Therefore, the expressions are equivalent. Moreover, they match the function shown in the earlier slide, confirming that both expressions represent the same Boolean function. Finally, the properties and axioms of Boolean algebra can be used to manipulate a Boolean expression and derive an equivalent one. Here we demonstrate how the logical expression not A, and not B and A can be manipulated to obtain the equivalent expression A. In particular, we apply De Morgan's law followed by the absorption property. As you may recall, in the final slide of the previous lesson, we mentioned 2 possible approaches for proving each property of switching algebra. These 2 approaches correspond exactly to the methods shown in the current and previous slides. In fact, each property and even each axiom is defined in terms of an identity between expressions. Thus, we can prove such identities either by verifying their truth for all combinations of input values, for example by constructing the truth table, or manipulating expressions algebraically using previously established properties.